Have you ever looked at your phone and just wondered, how is this thing so thin but so incredibly powerful? Or how does a life-saving pacemaker get small enough to, actually fit inside a person? Well, the answer is this really clever piece of engineering that is, quite literally, bending the rules. We're talking about the rigid flex PCB. Let's dive. I mean, seriously, think about it. It's a question that pushes engineers to their absolute limits. We all want our gadgets to be impossibly thin, to fold in half, to be more powerful than ever. But how do you actually cram all that tech into such tiny, weirdly shaped spaces without it just, breaking? And that question right there is the heart of what we call the modern design puzzle. It's this constant tug of war between what we can dream up and the physical laws of, stuff. Yeah, we want it all, don't we? We expect mind-blowing performance from our phones, our medical gear, even our cars. But at the same time, we want them to be super sleek, feather light, and fit into these complex 3D spaces that are anything but a simple, boring box. The thing is, the old way of building electronics just can't hang anymore. Taking a bunch of stiff, flat circuit boards and connecting them with a tangled mess of clumsy, delicate wires, that's a recipe for disaster. It's bulky, it's fragile, and it puts a hard stop on any kind of real design innovation. So, to really appreciate the solution, we first have to understand the two classic and kind of limited options that engineers used to be stuck with. It's like a tale of two very different boards. Okay, so on one side, you've got your rigid PCB. This is the workhorse. It's strong, it's super stable, totally reliable. But just like the name says, it doesn't bend at all. Then on the other side, you've got the flex PCB. It's bendy, it's lightweight, great for squeezing into tight corners, but it can be pretty fragile and doesn't offer any real structural support. So the choice was always a trade-off. You could have strength or you could have flexibility. You just couldn't have both. Here's a great way to think about it. Your own body is an engineering marvel, right? You have strong, rigid bones, and they're connected by these amazing flexible joints that let you move. The old way of making electronics was like trying to connect your bones with nothing but flimsy little ribbons. You just know that system is doomed to fail. And that brings us to the hero of our story, the rigid flex PCB. This is the genius hybrid solution we've been waiting for. It seamlessly fuses the strong, stable parts of a rigid board with the bendy, adaptable parts of a flex circuit, all into one single unified piece. It's the bone and the joint built together right from the very start. So, what does this amazing combination actually do for us? Well, this is where the true power of this technology really starts to shine. It's a total game changer. Now, what's really cool here is how each of these benefits just sort of dominoes into the next one. As soon as you make a single integrated board, you instantly save space and slash weight. That means you get to completely eliminate all those bulky connectors and failure-prone wires, which in turn just drastically cuts down the total number of parts you have to worry about. And that is the absolute key takeaway. Every single wire, every connector, every solder joint you get rid of, that's one less thing that can break, period. By making the whole internal system simpler, you make the entire device fundamentally more reliable. Okay, that's the theory, which is great. But where is this stuff actually making a difference out in the real world? Let's take a look at how this tech is hiding in plain sight in the gadgets all around us. Just look at the smartphone you're probably holding, or that's sitting right next to you. The reason it can be so impossibly thin, yet absolutely jam-packed with cameras and sensors and raw processing power. It's all thanks to rigid flex circuits that are meticulously designed to use every last millimeter of space inside. And this is where it gets really serious. In life-saving applications. For medical devices like pacemakers, rigid flex PCBs make it possible to build them smaller and lighter than ever before. And look, that's not just about convenience. It means less invasive surgeries and a whole lot more comfort for the patient. It's a huge deal. The same advantages are absolutely critical in the world of military and aerospace tech. I mean, think about a satellite or a fighter jet. Every single ounce matters. Rigid flex technology allows engineers to build incredibly complex and reliable electronics that are as light and compact as physically possible. But actually making a circuit board that can bend thousands of times without breaking, well, it's not quite as simple as it sounds. It's really less of a factory assembly line and more like a work of art that demands incredible, mind-boggling precision. Right. This isn't just gluing a flexible piece onto a rigid one. The entire thing is built as one integrated unit from the ground up. And that introduces some really fascinating, really tricky engineering problems that have to be solved before you even think about hitting go. So, trying to make this perfect hybrid board throws up two huge challenges. First up is the shrinkage problem. The flexible parts are made from a material that can handle tons of heat and bending. Awesome. But when you use chemicals to etch the copper circuits onto it, the material physically shrinks. Not by much, but just enough to throw everything out of alignment if you're not ready for it. Second, you have the stress problem. Picture bending a thick book. The pages on the outside of the curve have to travel a longer distance than the pages on the inside, right? It's the exact same idea here. If all your copper layers in the bendy section are the same length, the outer ones get stretched super tight and can literally crack. So, how do you solve for the laws of physics?
Well, the fix for the shrinkage problem is all about incredible foresight. You can't fix this later. Right from the very first design file, engineers have to predict exactly how much that specific material is going to shrink. Then, and get this, they intentionally design the flexible part to be just a little bit too big. The whole idea is that after all the chemical baths are done, it shrinks down to the perfect size. It's like microscopic tailoring.
And the solution to the stress problem? Oh, it's just beautiful, elegant engineering. It's a technique sometimes called bookbinding. Just like a book's cover is a tiny bit bigger than the pages, engineers design each layer in the flexible section to be a fraction of a millimeter longer than the one below it. This gives the whole thing just enough slack to bend smoothly without putting stress on any single layer. They even carefully place the copper traces along what's called the neutral bend axis. That's the imaginary line right in the middle that doesn't get stretched or squished. It's that insane level of detail that makes our folding phones possible. So when you really step back and look at it all, you realize that a rigid flex PCB is so much more than just some clever component. It's the key that finally frees designers from the tyranny of the flat rectangular box. It's what lets them build technology that actually fits the shape of our lives. Which really leaves us with one last fascinating question to chew on. For decades, the shape of our electronics was dictated by the flat circuit board inside. But now that circuits can bend, fold, and twist into almost any shape we can imagine, what incredible new forms will technology take next?